Not all steel is equal. And in this explainer, we're diving into exactly why choosing the wrong grade of steel for a ship isn't just a minor oops, it's a literal life or death decision. You know, when you look at a massive cargo ship, it's so easy to just see one giant uniform hunk of metal, right? But the reality? A modern hull is a highly engineered patchwork of very specific alloys, each one placed with absolute precision.
I mean, take a look at these two plates. On the left, we've got grade A steel. On the right, grade E. If you were holding them right now, they'd look identical, they'd feel identical, but their internal atomic structures, totally different. If you choose the wrong grade for the wrong location, your ship is going to fail. And not from bad welding, actually, and not from a flawed design, but simply because the material itself fundamentally cannot handle the job it was given.
So you really have to wonder, what actually happens to a massive container ship if someone accidentally swaps these visually identical materials? Well, the results aren't just, inconvenient, they're catastrophic. A ship at sea faces absolutely immense forces, from crushing cargo loads to violent ocean waves to literally freezing Arctic temperatures. And all of those require very specific metallurgical responses. So let's break down exactly how shipbuilders solve this invisible puzzle.
All right, let's start with our first category, the ordinary workhorse, which is your ordinary mild steel, specifically IAS-CS grades A and B. Now, the baseline power level, if you will, for ordinary mild steel is anchored right at 235 megapascals. That number is its yield strength. Basically, it's the exact point where the steel stops just flexing and permanently deforms. And the vast majority of a ship's standard hull structure relies heavily on this baseline strength.
But even though grades A and B share that exact same yield strength, they're deployed in totally different ways. Grade A is your go-to for general hull plating, where the stress levels are relatively moderate. Grade B, on the other hand, steps in for the thicker sections where you need a bit more resistance to set and cracking. It's manufactured to have what engineers call improved notch toughness. Basically, a notch is just any sharp corner or flaw where stress likes to concentrate. Grade B is just much better at stopping a crack from forming at those points, which makes it the absolute superior choice for the thicker, more critical parts of a standard hull.
Moving on to Section 2, high stress, higher tensile. What happens when mild steel just isn't enough? Because think about it. When a ship rides massive ocean waves, it doesn't stay perfectly rigid. It acts like a giant beam, bending and stretching. To defeat that, we bring in our first invisible hero, higher tensile steel. We're talking yield strengths of 355 megapascals or more. This gives naval architects a massive upgrade in shear strength to handle those extreme bending loads. Because of that incredible strength, these steels are deployed very strategically to the most highly stressed regions of the ship. Take the upper deck of a container ship, for example. It sits way far away from the ship's neutral axis, which means it bears the absolute brunt of the stretching and compressing forces. You'll also see this higher tensile steel used in hatch combings and areas right near the keel.
And this really highlights a brilliant modern engineering solution. Using higher tensile steel actually reduces the total weight of the ship while keeping it structurally invincible. Back in the day, the old way to get more strength was just to use thicker and thicker mild steel. But honestly, that adds massive weight, it eats into your cargo capacity, and it burns way more fuel. Today, by using higher tensile steel, architects can specify thinner, lighter plates in those critical areas that give you the exact same, or honestly, even greater maximum strength.
Let's move into Section 3, fighting the cold fracture and the invisible threat of freezing waters.
So, here's a wild metallurgical concept. Steel has this critical limit known as the brittle to ductile transition temperature. As long as you stay above this temperature, the steel safely bends and stretches. But if you drop below it, say during a route through the North Atlantic or the Arctic, the steel suddenly becomes brittle. I mean, it can fail instantaneously, without any warning, literally shattering like glass. To put that into perspective, if we took a piece of standard grade A steel down to minus 40 degrees Celsius, it would shatter under pressure. But that grade E steel we talked about earlier, it safely bends. Why? Well, these notch-tough grades are manufactured with highly controlled compositions. They intentionally push that dangerous transition temperature way below the freezing waters the ship is actually going to operate in. So in places where the hull is thickest and the stress is highest, grade E acts as a literal failsafe, stopping a catastrophic split right in its tracks.
Which brings us to our final section, the right steel everywhere, a carefully calculated patchwork.
So to quickly recap this explainer, we've looked at the ordinary workhorse that is mild steel, how we defeat stress with higher tensile steel, and how we fight the cold using notch toughness.
This structural cheat sheet is great because it perfectly summarizes exactly where each material goes, completely based on the specific physical and environmental stresses it's going to experience. You've got your mild steel, grades A and B, forming the bulk of the whole structure. Then, your higher tensile steels, the 355 plus megapascal stuff, are placed at the upper deck and keel to absorb all that bending. And finally, your notch-tough grades, like D and E, are strategically placed in extreme cold water environments and in ultra-thick areas to prevent that terrifying brittle fracture.
All right, so the correct steel has arrived at the shipyard and it's been designated to its specific block. But, actually, before any of the sparks fly, it has to undergo some absolutely crucial preparation. It needs to be perfectly straightened, thoroughly cleaned right down to the bare metal, and properly primed.
So, I want to leave you with this final thought to ponder until we dive into our next explainer. If the difference between a ship floating and utterly shattering lies in invisible atomic structures, what other hidden engineering marvels are keeping us safe every single day? We trust these massive vessels to move the entire world's cargo, and yet their very survival depends on atomic-level decisions made thousands of miles away in a steel mill. Pretty mind-blowing, right? Stay curious, keep looking below the surface, and I'll catch you next time.